Hey everyone, how goes it? And welcome back to Computer Science 146. Today, we're going to talk about recursion. Now, before we can move on to more advanced data structures, we need to talk about this very interesting problem-solving technique, which is called recursion. Now, the way that we can look at this is recursion is a way that we can solve a problem by solving smaller versions of the same problem. This is a very common problem-solving technique that's used in a lot of different algorithms. Specifically, there is a set of algorithms called divide and conquer where recursion really plays a major role. One of the ideas of recursion is by solving a smaller version of the exact same problem, you can then use that solution in order to solve the larger problem. This in turn means that recursion requires an element called backtracking in order to return solutions to those smaller problems in order to solve the larger one. Now, in reference to coding, we're going to be developing what's called recursive methods. And the way that this is going to work is effectively, it is just a method that calls itself. This in turn means that recursion is very loop-like, but it is different than using like a while loop or a for loop. Now, as recursive methods are loop-like, we have to keep in mind that the way that we have to have this working is, first of all, we need some sort of halting condition. Just like with a loop, you don't want an infinite loop, or in this case, infinite recursion. Another important element to recursion is that recursive call. So where does the method call itself? Now over here we have a very simple example of a recursive method. And as we can see right here, we pass in some sort of parameter, which is a number, and we're just going to use that number to count down from that number until we reach 0. Now the elements that make this recursive is, first of all, we have this halting condition. So if this I is less than 0, we have to return. Now most importantly, we have the recursive call itself. This method calls itself and then subtracts 1 from this value and then calls the method. Let's go ahead and see this in code. Now going over to our IDE, the first thing we're going to do is I'm just going to write several recursive methods inside of one class. So I'm just going to call this simple recursion, as we're going to be implementing a lot of different algorithms that use recursion. Now we're also going to use import java util.scanner just so we have some user input, so we'll start right there. Now I'm going to implement that countdown recursive method. Public static void countdown int I. So we're first going to start out with that halting condition. If I is strictly less than 0, then we're going to return. But otherwise, we call system.out.println the value of I. Then we recursively call countdown with the value I minus 1. So now, to see this working, what I'm going to do is call this from my main method. The reason why we made this method static is so we can just directly call it from the main method. Static methods can call other static methods. So in this case, we're going to count down from the value 5. So running this, 5, 4, 3, 2, 1, 0. So as you can see, this works a lot like a loop, but as we are calling a method, we know that what happens inside of memory is this method is constructed and pushed on top of the call stack. The call stack works just like a stack. It is last in, first out. To get a better understanding of what's going on in memory, let's take a closer look at this method. So here we have the method implemented, and also to the side here we have our call stack in our memory. Now you'll notice the first method that is pushed onto our call stack is that main method. And to keep this consistent with the example that we just saw, the main method is going to call countdown with the value of 5 as I. So it's going to look similar to this. So now this method is being called by the main method with the value of 5. Once this is called, what happens is this is pushed on top of the main method. The main method stops running, that way we can push this method on top of it and start running it. So then let's start stepping through and see what happens. If I is less than 0, well 5 is not less than 0, so then we print out the value of 5 in our console down here, and then we recursively call countdown with I minus 1. When we get to this recursive step, it subtracts 1 from 5, and then pushes the method countdown with the value of 4 on top of countdown 5. Now running this again, 4 is not less than 0, so we print out the value of 4, and then we recursively call countdown with 4 minus 1, which is now 3. So after a couple of recursive steps, we end up with a call stack that looks like this. As you can see, each one of the values has been pushed into memory like this. And now I is negative 1. So then we go to here. If I is less than 0, and it is. Negative 1 is less than 0, so we don't print anything out, we simply return, which is going to immediately stop this method. Now, as this method has finished running, it is simply removed from the call stack, and so it is popped off. Once that method has been popped off of the call stack, we resume back to where it was called from. And as you can see, on top of the stack right now is the method countdown with the value 0. This is where it was called. 0 minus 1 is negative 1, so that's why we had a countdown of negative 1 right here. Now that that has completed, we resume back to where we left off in countdown 0. Now this method has also completed once we get past this statement, so it pops that one off. Then we resume back from where countdown 1 was, and so that gets popped off as well. Countdown 2, that gets popped off as well. Countdown 3, that's popped off as well, and after a few returns, we get back to where we initially called countdown here. And now, the first method that was called by the main method has finally completed, and so that's popped off, and we resume back to our main method. Recursion can be thought of like a loop. However, recursion in programming involves utilizing the call stack. That way we can have backtracking to solve a smaller version of the same problem, use that solution to solve the bigger problem. Recursion is commonly used in mathematics in order to develop algorithms. Now what we're going to do is look at these very common mathematical functions, see how they're recursively defined, and now implement them in code. The first mathematical function that we're going to look at is simply factorial. And the way that we define this is, if we have n factorial, if n is 0, then the factorial is 1. Otherwise, we recursively define n factorial as this given n minus 1 factorial times the original n, as long as n is strictly greater than 0. Now let's see what this looks like in code. Now, in order to keep this as simple as possible, I'm just going to go ahead and write the method for factorial and just call it from our main method. So entering down here, public static int. Now, unlike countdown, it did not have to return a value. We were just printing out values. However, factorial requires that we return values from a smaller version of the problem. This is why the return type must be int. Now from here, we're just going to call it factorial. and pass in an int value, which we'll just call number. Now we just write our statements that follow the mathematical function. So here it is. If the number is equal to 0, then we return 1. Now this is the strict mathematical way of defining it, but in order to safeguard a lot of our code, let's go ahead and bound it like this. If any number that is less than or equal to 1 is passed into this, then we just simply return the value of 1. Now otherwise, what we do is we return this number times the factorial of this number minus 1. And so that's it. That's how factorial works. Let's see a demonstration of this. Going back to the main method, I'm just going to comment out this call, and now I'm going to call system.out.println factorial with the number 3. Now, as this returns an integer value, we will print out the value of factorial 3. Running this, we get the value of 6. Which 3 factorial is 3 times 2 times 1, which is 6. Now this version of recursion is a little more complicated because now we have to assume that this method returns a value. Let's take a closer look at this inside of memory as well. Now going inside of here, we have our main method that has already been pushed onto our call stack, and this is what called factorial with the value 3. So as you can see here, now we have pushed the method factorial with the parameter 3 on top of the main method. Now running through this, if the number is equal to 0, well 3 is not equal to 0, so now we call return 3 times the recursive call factorial 3 minus 1, which is 2, and that gets pushed onto our call stack. Now we need to solve this problem, and as 2 is not equal to 0, now we have to return the value of 2 times the factorial of 2 minus 1, which is 1, and we push that onto our call stack. Now 1 is not equal to 0, then 1 times whatever this factorial is, 1 minus 1 is 0, we now push factorial of 0 onto our call stack. Now 0 is equal to 0, so now we have to return the value of 1 right here. This method did not recursively call itself, it ended. And so when the method has completed each one of its statements, that method is removed. It is popped from the call stack. Now in this case, it returns the value of 1 from where we left off. Removing that, now we're at this method once again. So we're multiplying the number 1 times whatever this return value was, which was 1. 1 times 1 is 1, and so this method returns 1. So as you can see, that method was removed from the call stack it had completed, and now we resume back from where we were called from. Now we have the value of the number 2. 2 times whatever this returned, which is 1, is 2. 2 times 1 is 2. So then we return that value back from where it was called from, which is here. Now we have 3 times 2, which is the value of 6, and then that value is returned to our main method. So this is why the system.out.println printed the value 6. Let's see a slightly more complicated recursive method finding the greatest common divisor, the GCD. Mathematically, we can define this function to look like this. So given a greatest common divisor, you're given 2 parameters. For a given parameter A, if the given parameter B is 0, then the GCD of this is always going to be the value of A. Alternatively, if this value is not 0, then the GCD of this is the value of b recursively a mod b. Let's see how this looks in code. Entering down once again, we're going to go ahead and create a public static int. Now, as we're finding the greatest common divisor, it does need to return a value. And we're just going to call it GCD. And to keep this consistent, we're going to have int a and int b. We're just going to follow how this is mathematically defined. So if b is equal to 0, then we return the value of a. Otherwise, we return the greatest common divisor with the value b and a mod b. And that's it. That's how we can find the greatest common divisor. This one adds in a little more complexity because now we not only have a mathematical function that is going to return a value, but it also requires multiple parameters in order to solve it. Sometimes figuring out what parameters need to be passed to each one of the recursive methods can be one of the hardest parts of defining a recursive method. Taking a look at something else that is recursively defined in mathematics, let's take a look at the Fibonacci sequence. Now, what you have in the Fibonacci sequence is given this position n, what is the value found at this position? Another way that you can look at this is the index. And what is the value of the Fibonacci number given this index? One way that we can start to define this is the Fibonacci value at index 1 and 2 are both the value of 1. Then from there, anything that is greater than those values is defined as whatever the value which was previous in this sequence plus the value that was previously in this sequence. So this is why if you start out with 1 and 2 as both being 1, the value of f of n is 3 is 2. 3 minus 1 is 2, and then 3 minus 2 is 1, so 1 plus 1 is 2. At index 4, you have 1 plus 2, which is 3. At index 5, you have 2 plus 3, which is 5. 3 plus 5 is 8. 8 plus 5 is 13, and so on. Now let's see how this works. Scrolling down a little ways, we're going to go ahead and create public static int, and I'm just going to shorthand this called Fibo with an int number. In this case, we're just going to follow the direct definition. If the number is equal to 1 or the number is equal to 2, then simply enough, we return 1. Now, otherwise, what we need to do is else return recursively calling Fibo with this number minus 1 plus the recursive Fibo with the number minus 2. So this is how we can calculate the value of a number in this Fibonacci sequence. This may not look like much, but this is where we can start seeing the benefits of using recursion. As we have it right here, we not only have one recursive call, but we have two recursive calls. This is taking the problem and dividing it in half, where we are following this branch to find the solution to this problem, and then adding it together with the solution of the second version of the same problem. By using it in this way, we can elegantly solve a lot of problems that may seem very difficult. The idea of recursion is if we can solve this large problem by solving smaller versions of the exact same problem, then we utilize it in this way. Recursion can also be utilized in order to solve these seemingly complex problems like drawing this example of a fractal and make it very simple and straightforward. Recursion is absolutely a powerful tool that we use to develop algorithms. And in some of the future definitions of these more advanced data structures, we are going to be using recursion in order to accomplish this. And with all that being said, I'll see you next time.